We present the Fastron, an online learning-based model and active learning strategy for proxy collision detection. There are many applications that rely on frequent collision checks, such as sampling-based motion planning, reward evaluation for reinforcement learning tasks, creating datasets for deep learning robot tasks, and approximating object interactions in physics and CAD simulations. Since these applications rely so much on collision checking, our question is, can we make a model for faster proxy collision checking? We essentially seek to create a configuration space model. In configuration space, or C-space, a robot with n degrees of freedom is represented as an n-dimensional point. Any obstacle in the workspace is represented as a shape in C-space denoting in-collision configurations. While planning is easier when the robot is represented as a point, obstacles in C-space are generally not easy to compute or model. The idea behind the Fastron algorithm is to use an updatable model that may be used as a proxy collision checker. The Fastron algorithm uses a discriminative model to represent the boundary of the C-space obstacle. The model is repeatedly and efficiently updated using information gathered from a simple active learning strategy. The advantages of the Fastron algorithm are its classification time is fast due to its sparse classification model, its training time is accelerated by fixing the most erroneous points first, and it provides a risk-averse model by padding C-space obstacles. Given the dataset of sampled configurations, the Fastron uses a kinematics-based collision detector as an oracle function to generate the true collision status labels, either in collision or collision-free. The dataset of sampled configurations, along with the updated collision status labels, are used to update the model representing the C-space obstacle boundary. The model is a weighted sum of Gaussians where the sign indicates the predicted collision status. As obstacles in the workspace move, collision statuses of points in C-space will change. Rather than using a kinematics-based collision detector on every point in C-space, a subset of points on which this slower oracle function is to be used is selected using a two-stage exploitation-exploration active learning strategy. On the left, we have a 3DOF robot in a dynamic workspace. The Fastron is able to quickly account for the changing environment and model C-space obstacle boundaries, as shown in the figure on the right. On a simulated 2DOF robot in a MATLAB environment, proxy collision checks take around 34 microseconds using the Fastron. On the other hand, a polygonal collision checker takes almost 5 times as long with one workspace obstacle, and up to 12 times as long with 5 workspace obstacles. This illustrates that the Fastron scales much better than kinematics-based collision checkers with increasing workspace complexity. On a simulated 7DOF robot working with C++, proxy collision checks take around 4 microseconds using the Fastron. With a low-fidelity polyhedral collision checker, collision checks take almost twice as long. With the high-fidelity collision checker, collision checks take at least 8 times as long as our method. We can also see that once again the Fastron scales much better than kinematics-based collision checkers with increasing workspace complexity. Since the Fastron may be used for fast proxy collision checking, the Fastron will accelerate motion planning when using sampling-based methods, even when working with redundant or high DOF manipulators or in dynamic environments. In summary, the Fastron algorithm provides fast proxy collision checking, uses a quickly updatable model for changing environments, scales better than kinematics-based collision detection with increasing workspace complexity, and pads C-space obstacles for a risk-averse model.